we're going to start talking about projectiles, and it's very similar to the kinematics work we've done the other day, and so we are going to gravity, so no other forces. Start over. These problems are going to look really familiar to the kinematics problems we did in first semester, and the only difference will be that now the object will be moving in not just one dimension, it'll be moving in two. So prior to this, we had looked at objects that were either moving along the ground or thrown straight up into the air. Now we can have objects that are moving in the air, but they're moving not just straight up, they're moving at an angle. So if you haven't already done the kinematics review, you should do that first and then come back and watch this video, okay? So let's go ahead and draw the path for an object that's thrown horizontally off a cliff. For today, we're going to limit ourselves to looking at projectiles that are launched horizontally. So it's still, the object, the projectile, will still be moving in the horizontal and the vertical direction, but we're not going to throw it at an angle just yet. We're just going to throw it horizontally. So what this is going to look like, and what you're going to see drawn, is if this is your projectile and you launch it horizontally, you're going to find that it makes kind of a little arc. And a lot of people think that this is a semicircle or part of a circle, but it's not. This is actually part of a parabola. Okay, and what we're going to see is that any object that's thrown horizontally is going to follow a parabolic path. Now let's talk about forces for a second. This kind of goes back to our dynamics unit. And this next question asks, what forces are acting on the object after it is released from the thrower's hand? And that's really key. That after is bolded for a reason. A projectile is defined as an object that is only under the influence of gravity, the force of gravity. So there won't be any applied force from a person throwing it. There won't be any normal force. There won't be any air resistance. There won't be any force from the ground when it hits the ground, because when the object hits the ground, it's no longer a projectile, and the physics gets a lot tougher. So we're going to limit ourselves to looking at a projectile from the instant it's released to the instant it hits the ground, because the force of gravity is the only force that can be exerted on the projectile. Okay, so based on this information that the force of gravity is the only force acting, remember from our dynamics unit that then that means the net force is only the force of gravity, and the force of gravity always acts down. Well, the acceleration is always in the same direction as the net force, so that means our acceleration is down. It's only down. Now I'm gonna jump ahead a little bit, but I'm gonna kind of spoil a little bit for you. And what that's gonna mean is that since the acceleration is only down, the velocity of the projectile is only changing in the vertical, the y direction. In the horizontal direction, the velocity is going to be constant. So that's going to be a big deal. And the reason we can state that is because what happens in the vertical direction is independent of what happens in the horizontal direction. They're independent of each other. Right, so we can think of those perpendicular directions as having no effect on each other, okay? So let's take a look at our projectile path, okay? And we're going to draw the acceleration vector. Now, we haven't talked much about vectors here. A vector is simply a quantity that we're going to draw, and it's going to have a magnitude, a size, and it's going to have a direction. And that's why we draw the vector, we draw the arrow. And we want to use that direction to show, okay, what is the direction, in this case, of the acceleration? Now we know the magnitude of the acceleration, hopefully, and again, I'm kind of spoiling a few things for you. Hopefully you remember that g is 9.8 meters per second squared, and it's always pointing down. So the magnitude of our acceleration is 9.8 meters per second squared, and the direction we're going to draw, this is down. So I can go ahead and draw an arrow down, and because g is always the same, I can draw the exact same vector, and I can just call that g, or I could call it a, okay? So any of those would work. So that is going to be the vector or the acceleration that the object is going to experience. Now, let's think about something. And this is a tough question. You're standing at the edge of a cliff overlooking the ocean, and you throw a rock straight out in front of you, horizontally. At the same instant that the rock leaves your hand, your friend drops a rock over the hill. Which rock hits the water first and why? So go ahead and pause the video, come up with an answer and explanation here why, and then come back to the video and we'll talk about our explanation. Okay, you might be surprised to find out that both rocks reach the ground at the same time. And that's really key. Now let's think about why. Okay, first of all, they're both released from the same height. So they have the same height. That's pretty obvious. They also have the same initial velocity in the vertical direction. Vertical is the up-down, sometimes called the y direction. And that velocity is 0. Because when we threw the rock horizontally, that means we gave it only horizontal velocity, no vertical velocity. Your friend did the same when they dropped the rock. And they also have the same acceleration in the y direction. Well, if two objects start at the same location, and they always have the same velocity, and they always have the same acceleration, they're always going to be next to each other. So those objects are going to hit the ground at exactly the same time. Now, if you don't believe me, and you shouldn't, if you don't believe me, go ahead and go onto our Canvas. If you're on Schoology, that's fine too. Go ahead onto Canvas and look at the video. It's called the drop and shoot video. And it basically shows the same thing where we throw an object horizontally and we drop an object at the same time. And you're going to see that they hit the ground at exactly the same time. So go ahead and do that now. All right, hopefully you believe me now that those two objects are going to hit the ground at the same time. So let's take a look at a couple of additional drawings. So both these drawings represent an object, a projectile, that's been thrown horizontally. And on the first drawing, I'd like you to go ahead and draw the total velocity. Now it turns out that the velocity, or the speed, but velocity is a better term, is always tangent to the curve. So the way we can draw this is pretty simple. We're going to draw it, and it's hard to draw without using your notability tools, but I can kind of draw it like this. Okay, that's not very good either. Let me try it one more time. There we go, that's pretty straight. Okay, and then I can draw a velocity vector here, maybe. It's not very straight, but I tried. And then I can draw another one here. Now what you want to notice from each of these is that the velocity vector is getting bigger. So the object's getting faster as it falls. There's nothing new there, nothing earth-shattering. Okay? And it's also changing direction. It started out going mostly horizontal, now it's going mostly vertical. Now we can break this vector into two parts. We can break it into a horizontal part and a vertical part. So let's go ahead, and on this second drawing, let's go ahead and draw just the horizontal part. Okay? So the horizontal part looks like this. And then at each spot, it's going to be exactly the same size. So it never gets any bigger because there's no acceleration in the x direction. Then we can go ahead and we can draw the vertical component. Well, the vertical component starts out really, really small, and then it gets bigger, and then it gets bigger as time goes on. So this gets larger. Okay, so our horizontal component stays the same. Our vertical component gets larger. So we can signify this by writing that the velocity in the x direction is always the same, while the velocity in the y direction changes. There's another video on Canvas. There's a ping pong video, so if you'd like to go ahead and watch that now, that would be a great idea. Then when you come back, we're going to do an example problem. So go ahead and get your calculator. All right, so let's take a look at a typical problem that we'll have with projectiles. So we have a tennis ball, and it's going to roll off of a table that's 0.75 meters high. And we know the velocity of the ball when it falls off the table is 1.5 meters per second. So let's go ahead and let's start off with a little drawing. So here is the table, and here is the tennis ball, and it's moving horizontally with a velocity of 1.5 meters per second. And I can put the height of the table in there. I can say, well, the table, they told me, is 0.75 meters. And we want to know how much time the ball spends in the air. So here's what we're going to do. We're going to go ahead and we are going to do a bunch of kinematics problems. So hopefully you remember your kinematics equations. But we're going to have to go ahead and we're going to have to separate out our kinematics problem into two different categories. We're going to do a kinematics problem on the horizontal side, and we're going to do a kinematics problem on the vertical side. So I always like to list out my variables. You should remember this from when we were in kinematics. So we have 5 variables. We have delta x, we have v initial, we have v final, we have a, and we have t. Now, on the x side, okay, we know a couple of things. First of all, we know that the acceleration is 0. So we don't really have to include that variable. Second, we know that the final velocity is always equal to the initial velocity. So we don't really need that either. So let's go ahead and let's get rid of both of those right now. We don't need this, we don't need that, and we don't need to call this initial velocity because it's just the velocity. And let's go ahead then and we'll move t up here. But we do want to make one other change. We do want to say that this is not just the initial velocity, it's the velocity in the x direction. So those are the 3 variables we're going to use in the x side, or the horizontal part of the problem. And we know that the velocity is 1.5 meters per second. We don't know anything about the time yet, and we don't know how far the ball is going to land. So if we look at our picture, right, and we draw our little parabola there, we know that this distance right here is going to be delta x, okay? Now, let's go ahead and let's do the same thing, and let's go ahead and look at the delta y side. So delta y is our change in position in the vertical direction. So again, we have to list our variables. We're going to call them change in y, or delta y. We're going to call them initial velocity, final velocity, acceleration, and time. But here's the deal. If we put a line down the center here, the variables on the right are not the same as the variables on the left, so we have to differentiate those. So we're going to say that this is not just an initial velocity, but it's the initial velocity in the y direction, and it's the final velocity in the y direction, and it's the acceleration in the y direction. We don't need anything up here with the delta y because that's already clear. Similarly, we don't need ty like that because the time is the only variable that is the same on both sides of the equation, because it's simply the time that the projectile is in the air. So the time on the left in the blue is exactly the same as the time on the right in the black. So we don't need to differentiate that, okay? So now we can fill in what we know about what's going on in the y direction. Now I should know delta y. I should know how far it goes down. And I'm betting that if you put 0.75 meters, right, you would not be surprised. Here's the thing though, we have to be careful with our direction. Since the ball is going down, I assume down is negative, so I know my delta y is negative. I also know my initial velocity in the y direction is 0, because all of that 1.5 meters per second was directed to the horizontal. You might be tempted to put that the final velocity in the y direction is 0 as well, but it's not. It does not hit the ground with 0 velocity. Projectiles will not hit the ground with 0 velocity. So I put question mark. I bet you remember the acceleration in the y direction. This is our favorite number, 9.8 meters per second squared, and it does have to be negative because the acceleration is down, right? The Earth pulls down, the net force is down, so the acceleration is down, and we know that that's negative, and we don't know the time. Well, remember, if I know any 3 variables, I can find the other 2. So I'm going to stick to the y side because I know the most about what's going on in the y side. And I'm going to go ahead and I'm going to write my equation. And I think I'm going to use the position equation, if you remember that. Delta y is v initial t plus 1/2 at squared. I know my initial velocity is 0. So now I can plug in my other unknown, my other knowns. 0.75 meters equals 1/2 times negative 9.8 meters per second squared times time squared. Go ahead and plug that into your calculator, see what you get, and then come back and check the results. All right, you should have gotten the time is 0.39 seconds. And that's what they were asking for in the problem. That's how much time the ball spends in the air. This next part is asking how far from a spot on the floor directly under the edge of the table will it land? So now we have to go back to the x side of our table here, our problem-solving table. And we can use another position equation. Delta x is vxt plus 1/2 a in the x direction, t squared. I added those x just to be clear. But we remember, and this should really be a v initial x, but we know they're the same. We know the acceleration in the x direction is 0, so delta x is just equal to the velocity in the x direction times time. Well, we know the velocity in the x direction is 1.5 meters per second. And we found the time over on the y side, and it has to be the same, 0.39 seconds. So we should be able to see that the change in x, or the distance the ball travels in the horizontal direction, is about 0.59 meters. There we go. That's it. Okay. If you keep looking and go down one page, you're going to find that there's a bunch of practice problems. You should try those practice problems, and then you can check the key on Canvas. If you have questions, you can always come in and meet with me, or if you have a different teacher, that teacher as well. All right? Good luck with these projectile problems. See you soon.